Infrastructure development for Lunar Nuclear Plant by 2025, a $3 billion investment. Overview of the project. On April 24, 2025, China announced a groundbreaking initiative to construct a nuclear power plant on the Moon, representing a $3 billion investment aimed at establishing a sustainable energy source for future lunar missions. This ambitious plan is structured into 4 distinct phases: launch vehicle preparation, on-site construction, reactor assembly, and the integration of advanced technologies such as robotics and artificial intelligence (AI) for precision engineering. The Lunar Nuclear Power Plant aims to support long-term human presence on the Moon and facilitate deep space exploration by providing a reliable energy source. As space missions become increasingly complex, the need for sustainable and efficient energy solutions has never been more critical. The proposed plant will harness nuclear technology to meet these needs, marking a significant milestone in space infrastructure development. Investment breakdown in phases. Phase 1: Launch vehicle preparation. The first phase involves the preparation of launch vehicles capable of delivering the necessary components to the Moon. This includes the design and construction of rockets equipped with advanced propulsion systems, ensuring that they can withstand the rigors of space travel and deliver heavy payloads to the lunar surface. The investment in this phase is crucial as it lays the groundwork for subsequent construction activities. Phase 2: On-site construction. Following the successful launch of the vehicles, the second phase focuses on on-site construction of the nuclear plant. This phase involves establishing a base camp for workers and deploying robotic systems for the assembly of the plant infrastructure. The use of robotics will minimize human exposure to harsh lunar conditions and enhance precision in construction, a vital aspect of building a nuclear facility. Phase 3: Reactor assembly. The third phase centers around the assembly of the nuclear reactor itself. This will involve transporting reactor components to the Moon and utilizing advanced AI systems to ensure that the assembly process is executed with precision. AI algorithms will assist in monitoring construction progress, conducting safety checks, and optimizing operational efficiency. Phase 4: Integration of advanced technologies. The final phase will focus on the integration of advanced technologies, including AI and robotics, into the plant's operations. This includes the development of automated systems for reactor monitoring, maintenance, and troubleshooting. The goal is to create a self-sustaining power plant that can operate with minimal human intervention, reducing the risk associated with human error in a high-stakes environment. Application of AI and robotics. The integration of AI and robotics into the Lunar Nuclear Plant project is a key feature that sets it apart from traditional nuclear facilities. Advanced robotics will facilitate construction and maintenance tasks in the extreme lunar environment where conditions are harsh and unpredictable. Robots will be equipped with sensors and tools capable of performing intricate tasks such as welding and assembly without the need for human oversight. AI will play a vital role in ensuring operational efficiency and safety. By leveraging machine learning algorithms, the plant's systems can learn from operational data and optimize performance over time. This includes predictive maintenance capabilities where AI systems can anticipate equipment failures and schedule repairs proactively, thereby minimizing downtime. Safety and regulatory considerations. As with any nuclear project, safety is of paramount importance. The development of a lunar nuclear power plant raises several unique safety and regulatory challenges. Given the remote location and the potential consequences of a nuclear incident, stringent safety protocols will be established. This includes comprehensive risk assessments, emergency response plans, and continuous monitoring of environmental conditions. Additionally, international cooperation will be essential in establishing regulatory frameworks governing the use of nuclear technology in space. Engaging with global organizations and adhering to best practices will help ensure the safe and responsible development of nuclear energy on the Moon. Comparison with current developments in AI and nuclear facilities. While the Lunar Nuclear Plant project is groundbreaking, it is essential to recognize ongoing advancements in AI applications within existing nuclear facilities on Earth. For instance, the Diablo Canyon nuclear facility in California has started integrating AI tools such as Atomic Canyon's Neutron Enterprise to assist workers in navigating complex technical documents related to nuclear regulations. This initiative highlights the potential of AI to enhance operational efficiency and regulatory compliance in traditional nuclear settings. Key similarities and differences. 1. Investment in phases. Both the Lunar Project and the Diablo Canyon Initiative emphasize significant financial investment in structured phases for implementation. 2. AI integration. The application of AI is a common theme with both projects, exploring how advanced technologies can enhance operational efficiency and safety. However, the Lunar Project emphasizes robotics and AI for construction in a hostile environment, while Diablo Canyon focuses on AI for regulatory compliance in an existing facility. 3. Safety concerns. Both projects face scrutiny regarding the integration of AI in sensitive environments. There is a recognized need for regulatory frameworks to govern AI use in nuclear facilities, whether on Earth or in space. Timeline of events for Lunar Nuclear Plant development. 2023. Announcements of the Lunar Nuclear Power Plant initiative begin to surface, highlighting China's intentions to lead in lunar infrastructure development. 2024. Preparations for launch vehicles commence, focusing on designing rockets capable of transporting nuclear components to the Moon. Early 2025, construction teams including robotic systems are deployed to prepare the lunar site for building the nuclear plant. Mid-2025, assembly of the nuclear reactor begins, utilizing AI for precision and efficiency. Late 2025, full operational capabilities are expected to be demonstrated, showcasing the Lunar Nuclear Plant's potential as a sustainable energy source. Conclusion. The development of a lunar nuclear power plant by 2025 represents a transformative step in space exploration and energy sustainability. With a $3 billion investment structured across 4 phases, this project is poised to leverage advanced technologies like robotics and AI to establish a reliable energy source on the Moon. As the initiative progresses, it will not only enhance our capabilities for future lunar missions but also pave the way for the responsible use of nuclear technology in space. In parallel, ongoing developments at existing nuclear facilities such as Diablo Canyon illustrate the gradual integration of AI in the nuclear sector, emphasizing the importance of balancing technological advancement with safety and regulatory considerations. Together, these initiatives mark a new era in the pursuit of sustainable energy solutions both on Earth and beyond. The content presents several counterintuitive elements regarding the development of a lunar nuclear power plant and the integration of AI in nuclear facilities, particularly at Diablo Canyon. Here are some of the counterintuitive points identified. 1. AI as a cautious addition. While AI is often viewed as a disruptive, transformative force capable of completely revolutionizing industries, its current application at Diablo Canyon reflects a highly cautious approach. The AI tool Neutron Enterprise is limited to assisting workers in navigating regulatory documents rather than making operational decisions. This contrasts sharply with the broader public perception that AI will soon take over complex decision-making roles in various fields, including nuclear energy. 2. Positive reception in a cautious context. Despite the history of nuclear facilities facing significant scrutiny and public skepticism, the deployment of AI at Diablo Canyon has received a positive reception from some lawmakers and industry experts. This acceptance is surprising given the potential risks associated with AI in sensitive environments, indicating a shift in how technology is perceived in high-stakes industries. The expectation is that AI can enhance efficiency without compromising safety, which runs contrary to the typical narrative that automation in high-risk sectors is inherently dangerous. 3. Lunar plant feasibility versus current operations. the ambitious timeline for establishing a lunar nuclear plant by 2025 contrasts with the existing struggles of nuclear facilities like Diablo Canyon, which is slated for decommissioning. The notion that a new nuclear facility could be successfully implemented on the Moon while existing plants face closure highlights a counterintuitive disparity between aspirational technological advancement in space and the difficulties of maintaining nuclear energy infrastructure on Earth. For limited AI use in high-stakes environments, the expectation that AI will not be used for operational decision-making in nuclear power plants for an extended period seems at odds with the rapid pace of AI adoption in other sectors. This reveals a nuanced understanding of the limits of technology in contexts where safety and regulatory compliance are paramount, suggesting that the nuclear industry may prioritize human oversight over automation longer than other industries. 5. AI as a helper, not a decision-maker. The developers of AI tools like Neutron Enterprise explicitly state that they do not want AI to make decisions regarding plant operations, which contrasts with the general belief that AI will increasingly take on more responsibilities in various sectors. This admission underscores a recognition of the unique challenges and risks associated with AI in the nuclear sector, suggesting a more conservative approach to technology integration than commonly assumed. 6. Regulatory concerns versus innovation. The tension between the need for regulatory oversight and the desire for innovation in AI applications is particularly pronounced in the nuclear sector. While many industries push for rapid technological advancement with fewer regulations, the nuclear field's inherent risks call for stringent oversight. This duality is counterintuitive because one would typically expect industries to advocate for fewer restrictions to foster innovation, yet here there is a clear push for more regulations to ensure safety. 7. Trust in technology versus historical precedents. The deployment of AI in nuclear settings is met with both optimism and caution, reflecting a trust in the new technology despite the historical context of nuclear accidents. The juxtaposition of the perceived safety of advanced AI tools against the backdrop of past nuclear disasters illustrates a complex relationship between technological advancement and historical caution. These counterintuitive aspects reveal deeper insights into the challenges and dynamics of integrating advanced technologies like AI in critical sectors such as nuclear energy, especially in the context of ambitious projects like lunar nuclear power plants. The report on the development of a lunar nuclear power plant by 2025 and the integration of AI at the Diablo Canyon nuclear facility contains critical insights that are often overlooked. Here I will identify and elaborate on significant content that deserves more attention, focusing on its implications for future energy strategies and regulatory frameworks. 1. Investment in lunar nuclear power plant. The ambitious $3 billion investment for the lunar nuclear power plant is not merely a financial figure, it represents a paradigm shift in how we approach energy production in space. The four-phase project involving launch vehicle preparation, on-site construction, reactor assembly, and the use of advanced technologies signals a commitment to establishing a sustainable energy source for future lunar missions. Significance: this investment could set a precedent for international collaboration in space energy initiatives. It emphasizes the potential for establishing a permanent human presence on the Moon, which could facilitate deeper space exploration and possibly serve as a testing ground for technologies needed for missions to Mars and beyond. The geopolitical implications of such advancements are profound, as nations vie for leadership in space technology and exploration. 2. Advanced robotics and AI utilization. The project's reliance on advanced robotics and AI for precision engineering is a noteworthy point. While many reports focus on the financial and logistical aspects of the lunar nuclear plant, the technological advancements in AI and robotics are crucial for the success of such a project. Significance: the integration of AI and robotics can drastically increase efficiency and safety in the construction and operation of the plant, especially in the harsh lunar environment. This technology could lead to innovations that might be applicable on Earth, improving energy infrastructure and operational efficiency in various sectors. Moreover, the use of AI in a nuclear context raises questions about autonomy in critical systems, which could have far-reaching implications for the energy sector and regulatory practices. 3. Regulatory and safety concerns. The report highlights ongoing discussions regarding regulatory frameworks for AI in sensitive environments like nuclear plants. While many might overlook this aspect, it is of utmost importance. The use of AI in the Diablo Canyon facility, for instance, is currently limited to document retrieval, a relatively low-risk application. However, concerns about future AI applications in decision-making roles remain. Significance. This regulatory discussion is crucial as it could shape the future of AI deployment not only in nuclear facilities but across various industries. The need for stringent oversight and safety protocols is paramount, especially in sectors with high stakes like energy. As AI capabilities evolve, so too must our approaches to governance and risk management. 4. Local versus global perspectives on nuclear energy. The report outlines a dichotomy between the global ambitions of establishing a lunar nuclear power source and the local regulatory challenges faced by existing nuclear facilities like Diablo Canyon. While the Lunar project aims for energy independence in space, Diablo Canyon's integration of AI reflects a more cautious approach due to its operational context. Significance. This contrast illustrates how local regulatory frameworks can significantly impact technological innovation and deployment. The lessons learned from Diablo Canyon could inform global approaches to nuclear energy, particularly in regions where nuclear facilities are being reconsidered or decommissioned. Engaging stakeholders at various levels, local, national, and international, will be essential for the successful integration of new technologies in nuclear energy. 5. Public perception and trust in AI. The cautious stance taken by lawmakers and industry leaders regarding AI's role in nuclear facilities reflects a broader societal concern about the safety and reliability of AI systems. The report mentions that stakeholders express reticence about fully integrating AI into operational roles at nuclear plants, advocating for guardrails to ensure safety. Significance. This highlights the critical need for public trust in technologies that have potential risks. Engaging with communities and creating transparent processes for AI integration can mitigate fears and promote acceptance. As AI becomes more prevalent in energy systems, addressing public concerns will be vital for the successful implementation of these technologies. 6. Future of nuclear energy and AI integration. The discussion about the potential expansion of AI uses at Diablo Canyon, albeit with caution, opens a broader conversation about the future of nuclear energy. The report indicates that while current applications are limited to information retrieval, there is a vision for more extensive use of AI in operational contexts. Significance. The potential for AI to enhance operational efficiencies in nuclear energy could lead to a renaissance in the sector, especially as the world seeks to transition to cleaner energy sources. If managed properly, the integration of AI could revitalize public and governmental support for nuclear energy as a viable, sustainable option. Conclusion. The report on the Lunar Nuclear Power Plant and the developments at Diablo Canyon presents a rich tapestry of opportunities and challenges in the intersection of nuclear energy and advanced technology. By focusing on the overlooked aspects of investment, technological integration, regulatory frameworks, public perception, and the future of nuclear energy, we can better understand the implications of these initiatives. As we move towards a more technologically integrated energy landscape, these discussions will be vital in shaping policies and practices that ensure safety, sustainability, and public trust. 1. Investment in phased development. The ambitious project for a lunar nuclear power plant represents a significant investment of $3 billion structured over 4 distinct phases: launch vehicle preparation, on-site construction, reactor assembly, and integration of advanced technologies. This phased approach allows for systematic development, ensuring that each stage is completed before advancing to the next, which is critical for managing the complexities associated with space infrastructure projects. 2. Integration of AI and robotics in engineering. The utilization of advanced robotics and AI for precision engineering is a key highlight of the Lunar Nuclear Project. These technologies promise to enhance operational efficiency, improve safety, and reduce human error during construction and reactor assembly. The ongoing developments at the Diablo Canyon nuclear facility, where AI tools like Neutron Enterprise are being implemented to assist with regulatory compliance and document management, illustrate the potential benefits of integrating AI into nuclear operations. This sets a precedent for similar applications in the lunar context, where remote operations will be essential. 3. Safety and regulatory frameworks. The discussions surrounding the integration of AI into existing nuclear facilities such as Diablo Canyon underscore the critical importance of establishing robust safety and regulatory frameworks. As AI technologies evolve, lawmakers and experts express concerns about potential risks associated with their deployment in sensitive environments like nuclear plants. The call for stringent oversight highlights the need for developing comprehensive regulatory guidelines to ensure that AI applications do not compromise safety and operational integrity. 4. Strategic implications for global energy independence. The development of a lunar nuclear power plant is not merely a technological endeavor, it also carries strategic significance for global energy independence, particularly for future lunar missions. By establishing a sustainable energy source on the Moon, China aims to position itself as a leader in space energy infrastructure, potentially influencing international space policy and collaboration. This initiative aligns with broader geopolitical interests and the pursuit of energy independence beyond Earth, emphasizing the project's relevance in the context of global energy dynamics. Here are 3 famous historical cases of significant infrastructure development that are similar to the ambitious plans for a lunar nuclear power plant. 1. Apollo Program 1961–1972. The Apollo program was a series of space missions conducted by NASA with the primary goal of landing humans on the Moon and returning them safely to Earth. Initiated in 1961, the program represented a monumental investment in technology and infrastructure, culminating in the successful Apollo 11 mission in 1969, where astronauts Neil Armstrong and Buzz Aldrin became the first humans to walk on the lunar surface. The program required extensive planning, development of launch vehicles like the Saturn V, and the construction of facilities such as the Kennedy Space Center. It also involved advanced technology and engineering solutions, including the development of life support systems, navigation tools, and lunar modules. The program not only achieved its goal but also laid the groundwork for future space exploration and international cooperation. 2. The Manhattan Project 1942–1946. The Manhattan Project was a secret U.S. government research project during World War II aimed at developing the first nuclear weapons. It involved extensive investment, estimated at around $2 billion at the time, equivalent to more than $25 billion today, and was conducted across multiple sites including Los Alamos, Oak Ridge, and Hanford. The project required the assembly of a vast infrastructure for research, development, and production of nuclear materials. It also led to significant advancements in nuclear technology and engineering. The successful detonation of the atomic bomb in 1945 not only marked a pivotal moment in military history but also initiated the nuclear age, raising questions about safety regulation and the ethical implications of nuclear technology, issues that resonate with current discussions about AI and nuclear energy. 3. The Interstate Highway System 1956–present. Established by the Federal Aid Highway Act of 1956, the Interstate Highway System was a transformative infrastructure project that aimed to create an extensive network of highways across the United States. This initiative was driven by the need for efficient transportation of goods and military personnel during the Cold War, as well as improving economic connectivity. The project involved an estimated investment of $25 billion, over $300 billion today, and required meticulous planning, engineering, and construction phases often spanning decades. The interstate system has had lasting impacts on American society, economy, and urban development, facilitating interstate commerce and influencing patterns of migration and settlement. The integration of advanced engineering techniques and materials, along with considerations for safety and regulation, echoes the current challenges related to developing new energy infrastructure on the Moon. These historical cases illustrate the complexities of large-scale infrastructure development, including the necessity of significant financial investment, advanced technologies, and rigorous regulatory frameworks, all of which are relevant to the proposed Lunar Nuclear Power Plant project. Future outlook: predictions for Lunar Nuclear Plant development by 2025. The ambitious project to establish a lunar nuclear power plant by 2025, spearheaded by China with a $3 billion investment spread over 4 phases, represents a significant leap in space energy infrastructure. Here are predictions for the future of this groundbreaking initiative. 1. Successful phase completion by 2025. By the end of 2025, we anticipate the successful completion of all 4 phases of the Lunar Nuclear Plant project. The phases include launch vehicle preparation, development and testing of launch vehicles capable of transporting nuclear materials and construction equipment to the Moon. On-site construction, establishing the physical infrastructure required for the nuclear plant, including habitats for workers and facilities for reactor assembly. Reactor assembly, utilizing advanced robotics and AI for precision engineering to assemble the reactor and ensure safety standards are met. Operational readiness, testing the reactor and integrating it into the lunar base's energy grid. 2. Integration of advanced technologies. The integration of advanced robotics and AI will enhance construction efficiency and safety. By 2025, we expect significant strides in robotic systems, deployment of autonomous robots capable of performing complex construction tasks in the harsh lunar environment, reducing human risk and increasing precision. AI in operations, the use of AI for monitoring reactor performance and predictive maintenance, ensuring optimal operation and safety. 3. International collaboration and regulation development. As the project progresses, we foresee increased international collaboration in lunar exploration and energy development. Key predictions include regulatory frameworks, establishment of international standards and regulations for operating nuclear facilities on the Moon, addressing safety, environmental concerns, and security. Partnerships, collaboration with other nations and private entities interested in lunar missions will likely emerge, facilitating shared technology and resources. 4. Economic and resource implications. The Lunar Nuclear Power Plant project could have significant economic and resource implications. Energy independence. The successful operation of a nuclear power plant on the Moon may pave the way for energy independence for future lunar missions. Reducing reliance on Earth-based resources. Resource utilization. The project could lead to advancements in utilizing local lunar resources, in situ resource utilization, such as extracting water from lunar ice for use in nuclear processes or supporting human habitats. 5. Impact on future lunar missions and colonization. The establishment of a lunar nuclear power plant will likely bolster future lunar missions and the potential for colonization. Sustainable energy supply. The plant will provide a reliable and sustainable energy source for future lunar bases, enabling longer missions and supporting a growing human presence. Infrastructure development. As energy needs grow, additional infrastructure projects may be initiated, including habitats, research facilities, and transportation systems, leading to a more robust lunar economy. 6. Challenges and cautionary measures. Despite the optimistic outlook, several challenges and concerns must be addressed. Safety and environmental concerns. Ensuring the safety of nuclear operations on the Moon will require rigorous testing in compliance with international safety standards. Public perception and ethical considerations. Engaging with the public and addressing ethical concerns regarding space nuclear technology will be crucial in gaining support for the project. 7. AI and robotics in nuclear operations. Drawing parallels from developments at the Diablo Canyon nuclear facility, the integration of AI and robotics in lunar nuclear operations could evolve. Operational optimization. AI tools similar to Neutron Enterprise may emerge to assist in real-time decision-making and operational efficiency at lunar facilities. Future AI applications. As trust in AI grows, we may see expanded applications including automated safety checks and emergency response systems, ensuring a high level of operational integrity. 8. Broader implications for space exploration. The Lunar Nuclear Plant may set precedents for future space exploration initiatives. Mars and beyond, lessons learned from the Lunar Nuclear Project could inform the development of nuclear power solutions for missions to Mars and other celestial bodies. Commercial space ventures. The project may stimulate interest and investment from private companies in space energy solutions, leading to a new era of commercial space exploration. Conclusion. The Lunar Nuclear Plant project represents a pivotal moment in space exploration and energy development. By 2025, the successful completion of this initiative could revolutionize not only lunar missions but also the broader landscape of energy production in space. As technological advancements continue and international collaboration grows, the future of lunar energy independence appears promising, albeit with the need for careful consideration of safety and regulatory frameworks.